My name is Diplaxmi Rane and my roll number is A021. In this video, I'll be explaining how to create a comprehensive and interactive Power BI dashboard that visualizes global earthquake activity. This dashboard will allow us to explore the earthquake data from multiple perspectives, such as magnitude, depth, location, month, and year, to better understand seismic patterns across the world. By using different Power BI visuals like maps, bar charts, area charts, histograms, and scatter plots, we will transform a large raw data set into meaningful insights. Through this dashboard, we can identify high risk regions, observe long term trends, and analyze the relationship between earthquake depths and magnitude. Overall, this project helps us interpret complex geological data in a clear, visual, and interactive way. Next are the objectives. The first objective is to analyze global earthquake trends. Second, to visualize earthquake distribution geographically. Third, to study magnitude and depth patterns. Fourth, to identify seasonal or yearly variation. Fifth, to simply complex seismic data. 7. To support research and decision making. 8. To enable interactive data exploration. And last, to assist in risk assessment and awareness. Now, this is a dashboard that I have created that visualizes total earthquakes from 1900 to 2040. As you can see, the dashboard includes several visuals, two sliders, one for magnitude type and another for the year, a card displaying total earthquakes, bar chart showing earthquakes by magnitude and by month, an area chart for earthquakes by year, a histogram for depth, a scatter plot showing the relationship between the depth and the magnitude, and finally a map chart to visualize earthquake location. Before we start building the dashboard, let's take a quick look at our dataset. Here we have multiple columns, the time and date of each earthquake, latitude, longitude, depth, magnitude, and magnitude type. There are also several columns we won't be using, so we can just remove them later. We have an ID column for each earthquakes and an updated date, place, information, and type column. This last column will be used later when we create the histogram. Now let's begin to the dashboard that I have created. First, on the top left, you will see we are filtering specifically for magnitude type MB. For those unfamiliar with seismology, this stands for body wave magnitude. This is a specific way of measuring the energy of an earthquake, typically used for teleseismic event. Next to that, look at our timeline. We are covering a massive data set ranging from May 1900 all the way to March 2014. This is our century of data, which gives us a very robust historical baseline. Let's look at the top right. Based on the filters we have selected, our total sample size is 754 earthquakes. This is our universe of data for this season. Now, moving to the first chart of the left, total earthquakes by magnitude. This bar chart gives us a frequency distribution. Interestingly, this isn't a perfect curve. We see a bimodal distribution, meaning there are two distinct peaks. The first peak is at magnitude 6 with 131 records event. There is a deep and there is a second significant peak around magnitude 7 which with 103 events. This suggests that for the specific magnitude type MB, we are capturing a high volume of moderate to strong earthquakes rather than just a small decline as magnitude increases. Moving to the center of the dashboard, now the question arises, where is this happening? Looking at the total earthquakes by place map, despite a system warning banner we see at the top there, the data points are clear. We see the classic ring of fire pattern. Notice the heavy clustering along the western coast of South America, likely the Andean subduction zones. There is also significant activity moving through the South Pacific and Southeast Asia. We see smaller but notable clusters in Southern Europe and Central Asia. Slightly moving to the right, There is the depth and magnitude relationship scattered plot. This helps us to correlate how deep a quake is versus how strong it is. On the x-axis, we have depth up to 600 kilometers, whereas on the y-axis, we have magnitude. The takeaway here is a density. Look at that solid blue block on the left. The vast majority of our 754 earthquakes occur at shallow depth between 0 and 100 kilometers. While we do see deep earthquakes, they are much more sporadic and don't necessarily correlate with higher magnitude in this specific dataset. Let's drop down to the bottom row of the dashboard to look at the seasonality and verify our depth assumption. First, on the bottom left, total earthquakes by month. One might ask, is there an earthquake season? Generally, geology doesn't work that way. But looking at our data, we do see a spike in March with 94 events. The rest of the year is fairly consistent, hovering between 50 and 70 events per month, while March is an outlier here. Without further geological context, we would attribute this to a random variance rather than a seasonal pattern. Next, Next, in the bottom center, we have a depth histogram. This confirms what we suspected from the scatter plot above, but gives us precise numbers. Look at first bin, 417 earthquakes. That is more than half of our total data set. Occurred at a depth of 0 to approximately 50 or 60 kilometers. The next is bin drops to 187. By the time we get to the depth over 300 kilometer, the number becomes negligible. This is crucial for impact analysis as shallow earthquakes tend to cause more surface damage than a deeper ones. Finally, and perhaps most interestingly, let's look at the bottom right. Total earthquakes by year. This line chart tells us a fascinating story about the data collection. From 1900 up till roughly the 1970s, the line is relatively flat and low. However, look at the massive spike in the 1980s and 1990s. The count shoots up drastically, dropping off and then spiking again near the end of the timeline in 2014. As analysts, we have to interpret this carefully. Did earthquakes suddenly become three times more frequent in 1985? It's unlikely. What we are likely seeing here is the evolution of seismic detection technology. As the Cold War ended and global monitoring networks for nuclear testing and seismic activity improved, our ability to detect and catalog MB type earthquakes improved drastically. The spike represents better data capture, not necessarily a geological shift. Concluding, to summarize, this dashboard gives us a view of 754 significant seismic events. It tells us that while these events happen globally along major fault lines, they are predominantly shallow events. And while March appears busy and the 1990s appear volatile, we must always contextualize this data against the improvements in our detection technology. Thank you for your time.